Well, I'd like to thank the organizers for inviting me here. It's an interesting conference. I'm meeting interesting people, and I'm happy to talk about this subject. So it's about heterogeneous interfaces for teasing out the physics of embedded surface states. Now, the topological insulators, I was thinking I could talk more about that, and there will be some on topological insulators towards the end. But we're teasing out all sorts of new phenomenon in this work that we're doing, so bear with me. But let me start with a cartoon first. I have two substrates, a van der Waals crystals layered, or a semiconductor, and I bring down another van der Waals crystal, so the interface between these is heterogeneous, especially if they're two different materials. So we have a semiconductor van der Waals and a van der Waals, and in some cases I'll also include Bisco, superconducting Bisco, which is cleavable, and we can make similar structures with the superconductor. So I'll talk about a variety of these interfaces and the structures that we're studying with them. So from these, we're looking primarily at the interface by making connections to the top and the bottom of these structures. And we have, we can look at it in an electrical equivalent of either a resistance, a capacitor, or a diode. And the talk's mainly going to be about diodes, which act like resistors in forward bias and capacitors in backward bias. So we can measure both aspects when the junction is moderately doped and characterize the interface that way. We can change the temperature. We can add magnetic fields, which I'm not going to do in this talk, or we can chemically dope, which we've done. New physics. If we get new physics, we get very excited about it, and sometimes we don't know what we're going to get, but it comes accidentally, and that's always fun. And if you don't get new physics, we can sometimes get a device, walk away from it, and please our funding agents. So you'll see there are a number of possible applications of these kind of structures, and other people have been working on similar structures. So I want to start by explaining the Schottky barrier, because basically, I have to get used. Basically, we're going to be talking about Schottky structures. We're going to have in the semiconductors especially, we're going to have the doping such that we see the forward and bias diode characteristics. So okay, so for Schottky barriers, you understand in isolation the metal, semiconductor, and there's a Fermi energy here and a chemical potential here. When they're separated, the work function up to the vacuum level from the metal, and the work function up from the chemical potential to the vacuum level, and the electron affinity, the conduction band, the valence band. You connect them together, the equilibration of the chemical potentials, and you have the electrons. This is an n-doped semiconductor, so the bands are bending upwards. The electrons will flow up here into the electric fields enough to stop that diffusion, and you'll have a Schottky barrier height, Schottky barrier developed, and you'll get the diode characteristics. The other quantity I want to point out is we have this built-in potential. There's a Schottky barrier height phi sub b. Get used to this notation because I'll be plotting some of these. In fact, the first part of my talk, the first third or more, is going to be about Schottky barriers so that we really understand them and can understand the phase transitions we see in our when we're looking at like charge density waves or superconductivity, and even topological insulators. So this is the way, this is our schematic one. We take this, now I'm going to bring in, VBI here, and you can see that that you have, when you just look at the VBI, because it's equal to the, you get used to this. This distance here is the same as this distance here. This has the same curvature as the conduction band. And you have that the measure of the built-in potential is essentially equal to the work function difference between the metal and the semiconductor. That is true also for a PN junction. So that's a basic fact about Schottky barriers. If you can measure these work functions, you have VBI is a measure of the difference, if you know the work functions. Okay. Now, from the second schematic, which is the same, essentially, I want to now move the electron affinity up to the barrier region, and you can easily see now that the Schottky-Mott relationship, which relates the Schottky barrier height here to the difference between the work function in the metal and the electron affinity. And this is a very well-known relationship, the Schottky-Mott relationship, except for the fact that sometimes there can be surface states where the Fermi energy gets pinned to the surface states, and there's a high density of states there, and the Schottky-Mott relationship has to be modified by these high density of states where the Fermi energy gets lagged here. In some sense, the semiconductor doesn't recognize, if you have a high density surface states, it doesn't recognize the work function of the metal. Okay. And now, for high temperature, the process of getting over the barrier is usually by thermal emission. It's this over the barrier process, so you're at finite temperature. This is the width of the depletion layer, and this red dashed line represents the density of essentially your impurity levels. If you lower the temperature, this is silicon impurity band. We're going to use silicon impurities, and we're going to use mainly in this talk gallium arsenide because the silicon impurity level lies very close to the conduction band, around 6 millielectron volts away. So we can go down. We have lots of ionized donors in the conduction band, and the material conducts and doesn't freeze out, all the way down to 3 or 4 degrees Kelvin. So we can do low temperature experiments here. And when you lower the temperature, notice that what happens, this distance here, which is a difference between the conduction band edge and the Fermi energy, decreases. And if you lower the temperature down to it's 60 millivolts, this distance at room temperature, but it goes down to 4 at 4 Kelvin, and you can get into a tunneling regime. So in some sense, you have and we can go to low temperatures because we don't have freeze out. You can have over the barrier processes. As you lower the temperature, you have thermal field emission, and then you could have pure tunneling with maybe some thermal effects because you still have temperature in the problem. So the built-in potential, again, is to be remembered as the distance from the conduction band edge up to this height, looking in from the semiconductor. The Schottky barrier height is the distance from the Fermi energy up to the top. Actually, I might as well walk over here like everybody's been doing. So why did we become interested in it? It was because in this process of Schottky barriers, is because we accidentally made them. And it's one nice thing about being an experimentalist is you can be in the lab and you just try something out. And what we did was we took some graphite and just exfoliated it and pressed it against a semiconductor. And immediately saw, when we did a contacts to it, a diode. And so if it works for graphite, and you know that the first layer of graphite is graphene, it should work for graphene, and it did work for graphene. So we did a number of crude experiments, first just spring loading. The HOPG stands for highly oriented pyrolytic graphite. Just pressed it down. Sometimes we just got light flakes, and Van der Waals adhesion, where they just sucked down onto the substrate. And we even made a paint, which we could paint our barriers by making flakes, and they would line up and make a Schottky contact. Here's a typical junction. We make these plots on semi-log scale, and you can see this is a semi-log scale, and this is a linear scale, so you see a very strong forward bias and a very low current and reverse bias on this, on here and here. That's a log scale. That's a linear scale. That's silicon on graphite. Notice that it works for gallium arsenide very well. And important, on Schottky barriers, if you have a linear region here on a log scale, that enables you to use the thermal emission equation and get the parameters of the barrier very easily. And I'll show you how you do that. So it works for the silicon carbide polytype on graphite, and it works for gallium nitride. So it looked like a pretty universal technique for at least graphite on the semiconductors. And you'll see as I go through this talk that we've tried many different Van der Waals crystals with a similar technique. So it looked to us, like to us that we needed to learn a lot more about Schottky barriers and how they behave at low temperatures, because we want to study these phenomena at low temperatures. So it's so here's a big band, again the band schematic, and I want to show you about biasing. So here's zero bias right here. the alignment of the chemical potentials, the Schottky barrier height, and the built-in potential. It's always less than the Schottky barrier height. Forward bias is the applying negative charge of battery, make this difference here, and you lower the barrier height and you're in forward bias or high conduction, as you saw in the previous graphs. In reverse bias, you have a thicker barrier and low conduction. So that's basic picture diagrams of the diode behavior. And the Schottky-Mott relationship, just to remind you, without Fermi level pinning. So a few equations, and all of you have taken basic semiconducting courses. This is a diode equation, and it's exponentially sensitive, the current to the voltage. And there can be a series resistance, and you want to make sure that that's small. And this is sort of an empirical factor, which I'm going to ascribe some meaning to. It's called the ideality factor. And the saturation current is written in terms of some constants, a t squared, and the 0 voltage Schottky barrier height, which is, which I'll describe how we measure these things. And RS is temperature dependent, and so is this 0 voltage Schottky barrier height is temperature dependent. Okay, so the way we analyze this is at each temperature you plot the log of the current versus voltage and extract from the straight line proportion for voltages larger than the voltage drop caused by the series resistance, the voltage independent parameter eta. So notice that this exponential for the voltages we use is always a lot bigger than 1. For positive voltages, if I reverse the voltage, this term is very small, and the -1 dominates. That's why you get the diode. We extract these parameters from data like this. This is a gold N-type gallium arsenide Schottky barrier at different temperatures. The low temperatures being over to the right. This is linear. This is log linear. And we forward bias, reverse bias around 0 here. So 0 is you're around 0.6 of a volt, you get all the conduction you want. These slopes from taking the log, this is logarithmic over a reasonable range, so we can extract out from the slope of the log of the current versus the voltage, the ideality, so we can measure that from the slope. And we get cut off by this series resistance limit. So you want the series resistance to be small. Otherwise, if it's large, you'll get cut off at a lot lower current. So we want low current. And so let me just show you a little bit about what we do with our analysis. We rewrite the current voltage characteristic. And this was done by Cheng. It's called Cheng Analysis. You rewrite this. Essentially, this form is this equation, the thermal emission current rewritten. It's called Cheng's function. It's a linear function of current with a slope equal to the series resistance. So we have a way of measuring the series resistance and the intercept. And the intercept is a product of the ideality and the 0 voltage Schottky barrier height. This Schottky barrier height, remember, is an extrapolation to 0 voltage. That's why we call it the 0 voltage Schottky barrier height. It's not the real Schottky barrier, which would be under what we call flat band conditions. So let me explain that again. Here's the Cheng plots for the same junction. You can see it's very linear. This is very well behaved. We can extract from here a series resistance for our gallium arsenide at 300 Kelvin of 2.51 ohms. At 5 Kelvin, it's 1.64 ohms. Those are low resistances. And so that's why we get these nice logarithmic regions here. And you also get the product of the ideality and the 0 voltage Schottky height as 1.2 volts here and 1.22. Notice that this is not changing, and I'll give you a reason for that. So those are numbers which are sort of interesting. So let me continue. Here's a plot of actually just measuring the resistance of the barrier and it's very low resistance, and it comes up a little bit at low temperatures due to localization effects, but it's still very low resistance, all the way down to 5 Kelvin. We've gone down to even lower resistance. It's also important to understand that we can do capacitance measurements and in reverse bias. And so this is a well-known relationship which is solved by just showing that the density of ionized impurities is just constant in this depletion width. And you solve Poisson's equation, you get a shape for that curvature in the band, and you can derive using Poisson's equation the 1 over the capacitance squared goes proportional to the reverse bias voltage, and it has an intercept at the built-in potential. So we can measure the built-in potential when this is a nice linear plot, the 1 over c squared plot. V is a reverse bias. This is the dielectric constant, which we know. And N sub d is a donor density of ionized impurities. You can, by different wafers, have different impurity densities. So you plot 1 over c squared versus VR to get an intercept and a slope, which gives you the carrier, the impurity density. And these are our typical plots. There's one thing about these van der Waals junctions, and it's just nature's being kind to us. We almost always see nice linear plots with very nice intercepts. So we get VBI rather convincingly. This is for the gold N-type. This is not a van der Waals junction, but we happen to get it also for a gallium arsenide gold junction. And you can see that at various frequencies and different temperatures, you get an intercept of VBI here. There's not that much temperature dependence. And you can just read off the intercept. Remember, this is reverse bias. You can't go in this direction because you're going in the direction where you're beginning to pour electrons over the barrier, and you have too much current, so you can't make a capacitance measurement very accurately. Okay. How do we analyze this? This was done in the old days by Werner and Gutler, in the old days not too far long ago. But since we can go down to lower temperatures, and we can get the temperature dependence of our idealities and our zero voltage Schottky barrier heights to a lot lower temperatures. And the way we analyze it is similar to what Werner and Gutler did, is you assume that there's a distribution of barrier heights. That's reality. And that when you bias it in a forward direction, this distribution has a temperature dependence, and it also has a temperature dependence, but that becomes narrower. And eventually, when you go to high enough voltage, you get to what's called a flat band condition. That's the true barrier height. There's no curvature left, and electrons are just pouring over the barrier. So how do we can't go up that high because we run into our series resistance. Okay. So here's the substitution you make into the thermal emission equation. You take the inverse, and this is what Werner and Gutler did, and we're just doing it again. And you make this substitution. You assume that the VBI measurement is saturated. It comes up to a constant value. And especially at zero temperature, it slowly increases. You'll see that. And what we do is you assume that it's saturated, and where the bands are flat, at the flat band voltage, we're going to call flat band. There's no dispersion in the Schottky barrier heights. That distribution has become very narrow. And the following association holds. Essentially, your VBI, your built-in potential measurement, becomes a measurement of the average flat band voltage, which is essentially, it can be a function of temperature. And there's very little temperature dependence at low temperature. So this is an experimentally demonstrated result that our VBI saturated is a product of the temperature dependence of the ideality and the zero voltage barrier height. So essentially, one has a linear temperature. This has inverse temperature linear. This has temperature dependence. They cancel out, and I'll show you that. That was a surprise in this experiment. So here I'm coming to actual data and going to low temperatures. You see we're going down to 5 Kelvin. The Schottky barrier, the zero voltage Schottky barrier height starts off, and this is the region most people were in until they could go down to low temperature. But notice that it goes linear, and it goes linear and it intercepts 0. Okay, the zero voltage Schottky barrier height is going to 0. And the ideality, which is going up, your ideal junctions have close to ideality, close to 1, and it's going up. But when you plot the inverse of this, it's also linear and extrapolates to 0. So we're getting these two results because we can go to low temperatures and see. And this we see on all of our junctions, this linear dependence, and essentially that agreement with the linear dependence is canceling out in this relationship. So here's your coefficient describing the linear temperature dependence of the zero voltage Schottky barrier height. Here's the temperature dependence of the, of the inverse of the ideality, another slope. The product of these two is independent of temperature and gives you the flat band voltage, which you can show from this. I'm not going to go through all the analysis, but you can show that using that probability distribution and going through all the averaging over a Gaussian distribution over this thermionic equation. So that's what we see for gallium arsenide. Schottky barriers. Okay. This is plotting the 0 voltage Schottky barrier height versus temperature, and it's linear again, and it's, I'm just essentially repeating the data here, but I want to show you the inverse capacitance. So the important part about this is that in forward bias, we're measuring ideality and the 0 voltage Schottky barrier height and getting the flat band voltage without going up to that very high current where RS, the series resistance, would cause a voltage drop, and you just can't get there. So this is low voltage measurements giving us the flat band voltage, which you measure directly with capacitance, which is in reverse bias. And from these nice linear extrapolations, we get a good agreement with the intercept here with the calculated flat band voltage of 1.26 from the forward bias characteristics. So the whole point of this is that you can use both forward bias and reverse bias. One's a capacitance measurement, the other is a transport measurement, and check what the flat band voltage is. And that's, okay, now we get to some physics. We're going to use these techniques to look at the transition metal dichalcogenides. I'm showing a picture of graphene. The transition metal dichalcogenides have that we're going to look at. I'm going to talk about tantalum disulfide, titanium disulfide, and niobium disulfide. And same hexagonal sort of honeycomb structure, but with different atoms at the alternate sites. Oops. I thought somebody might eventually fall off here. It was not me. Because I'm sitting in the front row and watching people get very close to this. Okay. Let's look at tantalum disulfide. This is a fascinating material. This is a charge density wave material. This is a resistance as a function of temperature of tantalum disulfide. It exfoliates beautifully. It's a layered compound, van der Waals crystal. It's a non-commensurate CDW at above these temperatures. This is a cooling transition. This is a warming transition. It's a first order phase transition. And then as you go down to lower temperatures, you turn into the resistance goes up and it becomes a MOT. It converts to a commensurate charge density wave from a non-commensurate charge density wave. The melted MOT, this you might call a MOT, melted MOT stage with the Fermi level going through the conduction band, and here's an energy gap. So this is definitely an energy gap material at low temperatures. Okay, and the interesting thing about this material, and it's been studied in by lots of people, is it has these beautiful, they call them Star of David formation in the melted MOT state. These exist as isolated clusters, and there's a conducting medium between here. But when you cool down, it forms a really nice commensurate charge density wave with these, it's 13 atoms, and they're constricted in towards a central atom. Each star is 13 atoms, okay? 12 outer atoms constricted in a little bit towards the center. So that's our MOT phase, and we're going to look quickly at the band structure. That's the resistance, just to remind you. But what we're doing now is we're making Schottky diodes out of these by just taking the N-type gallium arsenide, peeling it, freshly cleaved, doing the same thing with A1T with a tantalum disulfide, and pushing it down, and silver paste. And this is the structure. This is the band structure that we're expecting. This is the semiconducting metallic phase where you have the built-in potential in a semiconductor. But remember, there's a MOT gap that's opening up as you cool it down, so the band structure becomes a little more complicated because there are two built-in potentials to measure. But that relationship that I told you about the built-in potentials being the difference between the work functions of the two materials is still holds here. It's a PN junction, if you want to think of it that way. And this is the capacitance for this structure, the inverse capacitance relationship. It goes like VBI. This becomes 0, extrapolates. But we now have two contributions. And it turns out that ND, the density of donors, this term is a lot smaller than this term, so we're essentially dominated. The band bending in the, here is a lot smaller than the band bending in the semiconductor. So we now are going to look at this structure. We've seen what happens in the resistance. Let's look and see what happens to the diode. Here we have, again, our current versus voltage. You can see a nice linear, log linear dependence. We extract here our idealities. We have a resistance which cuts us off up here, our idealities, and we plot 1 over the idealities for the cooling and warming. Okay, so cooling, the ideality is is going to a dip, and then it goes up. So this is the ideality is becoming larger as you cool down, but it has this dip. And the Schottky barrier height also has a region of hysteresis, which exactly overlaps the forward. So the forward bias almost fell off. The forward, this is temperature dependence, and from forward bias characteristics is these data. And let me show you the capacitance data. So covering and warming hysteresis is the same in temperature range as a hysteresis in R2, and that's indicated by this bracket. So we're seeing evidence in the diode at the interface, the evidence of the CDW. Now you think of a CDW as being in bulk, but you have to terminate the resistor, the charge densities at the interface. So what we're doing is measuring the CDW in a different way. We're measuring it as it appears at the interface of this Schottky barrier. And that's what these data represent here. Okay, and we're doing it from the forward bias characteristics. Okay, we can also do the same thing from the capacitance characteristics. This is going to the reverse bias and measuring it directly. And you see here, let me bring down first panel A here on the left. It's showing you the linearity and the nice extrapolations to VBIs. 1 over C squared to VBI at different temperatures. So we do this at different temperatures, and you could do it as a function of temperature. And we plotted the VBIs as blue squares and red triangles on this plot. And this is where the CDW is forming. And we've also, the panel B is transport and capacitance data are consistent with each other. So what the open squares are the product of, it's over here, the product of the ideality and the zero voltage barrier heights. Those are things we measure in forward bias, and we're taking the change in that product, and we know that that's essentially change in the flat band voltage, if you want to look at it that way. But these data overlap each other. The data determined in forward bias overlaps the data returned in reverse bias. So it's giving us, and the capacitance data, you can see, this is just measuring the capacitance itself, even though, and this is just showing that there's a capacitance increase here, which corresponds to a VBI decrease from that 1 over C squared equation I showed you versus was proportional, linearly proportional to VBI. So all the data are consistent, and the behavior in the resistance transition is replicated at the interface. And now we'd like to get a more detailed interpretation. Let me give the last thing. Oh, I'm talking about this. I just talked about this. Increase in capacitance on cooling implies a decrease in the VBI. Okay, so so here's a band diagram. Here's your and there's an interaction parameter. And what we're doing is using Ray Tung's theory about bond polarization. So there's an extra charge density at this barrier induced by the charge density waves, and we want to see how that affects the band structure. So there's an interaction term, which is related to this kappa here. These are the terms we've already talked about, and this is the band gap we put of the semiconductor. So we have the VBI, this dashed line. There's a extra interaction term from the charge polarization, and the VBI is reduced, as we saw experimentally, okay? And this is a picture of the interfacial region. Did the 10-minute sign go up? No. I have 10 minutes. It's now gone up. 5 minutes? 10, okay. Okay. So what happens when a transition metal I hope you all are convinced that we're seeing CDWs at the interface. You can ask me later. But what happens when a transition metal meets a superconductor? And as I said in the introduction, Bisco is cleavable and acts in many ways as a very beautiful surface. You can cleave it, and we can just press our tantalum disulfide against Bisco. We made 4-terminal devices where we have the tantalum disulfide is in the yellow. It's placed on top of the Bisco flake. It's not as beautifully sculpted as this picture is, but we get a tunnel junction, and we can measure it in 4 terminals. And so, and this is AFM pictures of the quality of our surface at the order of fractions of a nanometer flat. So what we have here is a superconductor against, and this is as a function of voltage. And these are we've made 5 different junctions with different transparencies. The lowest one is a transparency. These are low temperature data, 5 Kelvin. The lowest, this for those of you who do superconductivity, this is a proximity effect. There's essentially, from the Bisco, there is a gap induced into this Mott insulating phase of tantalum disulfide. And the proximity effect is measured by the doubling of the conductance in this region for a high transparent barrier. Low Z means high transparency. And what we are measuring from the structures in our current voltage characteristics are these energy gaps. This is deep in the superconductor. We have the bulk Bisco gap. The gap is reduced into a certain value at the interface. And then there's a gap that's induced. There's a discontinuous jump, and a gap that falls off into the tantalum disulfide. And eventually, as we go up to lower transparencies, this gap closes here, and it becomes more or less continuous. But there's still a proximity effect into the superconductor. So these curves are showing, you can see that this Andreev reflection feature disappears as you go up to less transparency. I'll go through the remark that this is a rather big gap, 20 millivolts. It's half the gap of Bisco. So we've induced high TC in this Mott insulating phase. And the CDW doesn't destroy it. If anything, it's coexisting with it. Whether it helps it or not, we don't know. So this is an example of inducing high TC superconductivity in a Mott insulating CDW phase. Here's again just the current voltage characteristic. You can easily see that the doubling of the conductance until you go out to, this is for a Z of 0.25 or a high transparent junction. And this is the normal state. So these are different temperatures. And we can do a lot of spectroscopy, which we've done. This tunneling spectroscopy, this is a current the differential conductance normalized to the normal state, superconducting normalized to normal state. And I don't have time to go over this, but we do spectroscopy and look for maximum. And we see in the second derivatives, as sort of stuff that Bill McMillan and John Rowell did in getting the phonon contributions to superconductivity. And the long and the short of it, this again is 5KO. I should show that it's high C strong coupling for the induced gap here. It's 5.8. So the gap is pretty big, and the TC is fairly high, as you'll see. So we see some double dip hump structures. I don't have time to go through this because I noticed I want to get to some other things. You can see that we did a lot of spectroscopy in identifying these features. And basically, we see 2 boson modes, 2 peaks due to bosons, one which is already known for Bisco, and the other one which has something to do with the CDW in there. So there's a boson mode that we can recognize in our tunneling data that's visible on our IV spectra. And I won't go into detail, except that one of these modes overlaps this mode here. This is for different transparencies. Overlaps. I have 5 minutes left. Thank you. And that mode overlaps with one that's seen in optics, in transmission optics by David Tanner and collaborators. The 25 millivolts is right here, this Phonon mode. So we believe that this is a mode that's involved in that second feature that we're seeing in the spectroscopic data. So that's a bit detailed, but it's showing that there's basically that you can induce a high TC gap in Normally, you do proximity effects in normal metals, but for somehow we're creating an instability in the Mott phase, and it's acting, it's receptive to superconductivity. Now, I want to look at second order CDW transitions. I'll go through this rather fast. We've looked at, so this is not with this same, these are CDW transitions enabled by strong electron-phonon coupling. And these are the resistance curves here. Whoops. Let's see, the resistance curves. I'm going back. Here's the resistance curves here. This is titanium diselenide, this is titanium diselenide, this is niobium diselenide. You can identify a CDW transition. We doped it with superconductivity. Here is the, with copper, it becomes superconducting. Notice that when it comes superconducting, the CDW disappears. And opposite to the case where we've induced a gap in the tantalum disulfide. So we take, does not coexist with CDWs. It's, when it's doped with copper. We've gone back to the pure titanium diselenide and the niobium diselenide, done our current voltage characteristics and our, and seen little features here, which again, just like in the tantalum disulfide, this feature mimics what we see in the conductivity resistance transitions. We do the capacitance measurements, and again, we do a comparison to a normal, this is a graphite counterelectrode, so that we can normalize these bumps. And when we normalize them, I'm going a little bit speedy here, but I just want to show you the final result. When we normalize these bumps that we see that titanium diselenide has a high, this is where the CDW starts. It's a semi-metal here. There's no CDW in this region. And we go through a peak, and it looks like the order parameter, if you want to think of their CDW order parameter, maximizes. Here, in niobium diselenide, the CDW order occurs at a much higher temperature than where we saw the peak, and you just see a peak. What we think this is showing a transition from short-range correlations to long-range correlations. You see a peak in both materials. Okay. So from these, we conclude that with lowering temperature, the chemical shifts. Now remember, all this is related to the chemical shifts. So where's the charge coming from? It's coming from the shifts in the Fermi energy, and there's a coherence increased correlation as you go to low temperature, as revealed by these data taken at the interface and directly measuring the shifts in the voltages or shifts in the Fermi energy by measuring VBI. And now I want to talk about finally the Bisco N-type gallium arsenide interface. So here we're taking Bisco instead of putting it against tantalum disulfide. And I'm just showing you again that we get this common feature of linearity, and 1 over this is linear also. So it's behaving just the same way as it did with the van der Waals materials. And what's interesting about the Bisco material is that we can measure capacitance. We see capacitance changes at the high temperature, where the pseudo gap presumably forms, but we also see some capacitance changes at high frequency. This is the transition of the Bisco at 90 Kelvin, and we don't understand this yet at all. That there's something going on in the superconductor. In fact, VBI for Bisco is higher than it is for all of our other materials. So there's something going on at the interface that's causing an additional flat band shift due to the Bisco, and there's some changes involved at the transition temperature, which may be related to screening lengths, et cetera. And that's not understood, but it's certainly evident in the experiment. It's always fun to show data which you don't understand. We can tunnel in these devices. So again, I said that, and we showed showing tunnel because we see the tunneling gap. This is a tunneling. This is for a the tunneling gap agrees with the Bisco gap here, these features here, and this 2 delta is in good agreement with Bisco, and we see single peak here due to the well-known Phonon mode in Bisco, or if you want to call it a Phonon mode. So we have done a lot of spectroscopy. This is silver. This is just looking at a piece of Bisco alone with silver on both sides and showing that the gap again is 4 delta, because we have 130 millivolts for that difference. So let me show one final graph. This is where topological insulators come in. if we can look at CDWs and we can look at superconducting states, our theory was we could look at the surface state of topologically protected surface states. We made a junction on bismuth Bi2Se3 on silicon. Now, silicon you can't cool down below 50 because of carrier freeze out, but this is one of the most beautiful junctions that we've seen. The linearity here is about 6 decades in current. However, this is not a good topological insulator. So our goal now is to get in other words, the Fermi energy cuts through the conduction band here. So when you analyze this, we're not looking at just the surface state on our counter electrode, but we're looking into the bulk. But it is a very nice Schottky junction. And that's quick conclusions. We've used Schottky barriers to study buried interfaces. We can go with gallium arsenide's ideal substrate, especially if it's doped with silicon. We can do tunneling and capacitance measurements on the same moderately doped Schottky barrier. So you understand the barrier very well, and tunneling gives you transport through it. Capacitance gives you the charge buildup at the barrier, and that's what's helping us here. We've studied superconductivity, CDW formation, and we'd love to study in more detail the topologically protected surface states and interfaces. We've addressed the physics of thermal field emission and tunneling and captured it in a surprisingly straightforward manner by using the thermal emission equation with the modifications of the eta and Schottky barrier height parameters. And we have promising control parameters, the magnetic fields for future work. First, there are a lot of van der Waals crystals out there. Magnetic field, layer thickness we can change. We can go from multi-layer. Our samples are multi-layer. I should have mentioned that. We haven't gone to single layer yet. We can change the doping density in the semiconductor, and we can even intercalate the van der Waals electrode. So I think there's a lot of room in these kind of experiments for exploring novel physics at interfaces. Thank you for your attention. Oh, I wanted to this is really important. Excuse me. My collaborators, and the ones in red have been really primary collaborators. These 3 students are with me now, and they're doing a lot of this present work. Okay.
Questions?
Thank you. Your conclusion that you're seeing or picking up the charge density wave transition through these capacitance measurements is based on this surface charge model, right? Mm-hmm. And what it should, implicate in terms of the capacitance or yes, the behavior of the junction. Does that rely on your charge density wave having a non-zero, the wave vector being non-zero on the stacking, in Z direction?
We are always going along the C direction, and yes, I think it does. I think the charge density wave has, yeah.
So if the modulation wave vector is in the plane, would that not work?
Apparently, on the 2 materials, the charge density with a vector is fixed, and we really have to worry about the magnitude and the phase of the CDW. But we can't individually address those in these kind of experiments, except for those peaks. If that's a coherence peak, that's doing sort of an average of the coherence, short range to long range as you cool it down.
So, but I'm trying to understand. So, are you saying that even if your CDW wave vector is in the plane, you would pick up this effect, or only if you have a component along the stacking, along your junction, your interface?
I believe it's along the plane, and the surface charge is uniform along the plane. I'm not positive about that. Okay. I have to say I'm not positive about that. There's certainly a bond polarization contribution to what we see. We're interpreting it in terms of that model, which means there's a charge difference.
Okay, could I ask you about about the modulate the charge density wave stuff again? When you were talking about this proximity effect, when you
oh yes, yeah.
And is in that particular compound, the tantalum disulfide, I think it was. Is there a spin density wave any nearby in the phase?
No, not that I know of. No. Yeah.
So the second question was, when you said you were talking about the Mott aspects,
What? About the.
I mean, my recollection from a long time ago about these transition metal dichalcogenides was you could describe them pretty well by one electron theory. Has that changed now?
This seems to have changed. Latest, and there's a lot of ARPAS studies of this material. There seems that there's more or less universal consensus that there's a Mott transition.
And how big are the U's? The Hubbard U's?
It's not a big gap. I don't know. I don't know the answer to that. Yeah. Yeah,
Okay.
they're there though.
And finally, in terms of the melted versus non-melted?
Pardon? Yeah, the melted versus the unmelted. That's yes. A
Is
nearly commensurate charge density wave going to a commensurate charge density wave. And that's seen in ARPAS and X-rays and electron microscopy. There's a lot of surface studies of this material. These structures, the Star of David structure is quite interesting.
Okay. Thanks very much.
Yeah.
So, yeah. So, do you try here?
Wave your
here,
hand.
Here,
Okay.
here. Sorry, sir.
That's all right.
So, do you try in the superconducting case? Do you
Yes.
try different dopings, going from the underdope to the optimally dope? And see the
No,
difference?
no. That's something we would love to do. Yeah. Do you mean to see what's happening at the interface? I
Yeah.
totally agree. Yeah. I
You
wish
did
there
it.
was. I would like there to be a higher temperature TC S-wave superconductor because the materials we're looking at is layered, and I can't say for sure that I think that this and we've used, by the way, we used analysis where you tunneling from a D-wave superconductor and doing proximity effect. There's some Japanese theorists that gave us that theory. But it'd be nice to look at S-wave superconductor and make it a simple problem. It's not,
Thanks.
yeah.